Right. We had an exercise last week, correct, boys? And we looked. I think that was exercise, the third exercise, where we should cover the fourth one today. And that was on. It was on the limiting reactant. Correct.
Yes.
All right. So what we're going to do today is we're going to be looking at the percentage composition and percentage yield. But before we do that, before we spend a little time on that, what I'm going to do is just go through a bit of the exercise of last week. So if you guys have that with you, um, you're welcome to obviously refer to that and follow along with me. Number 3. Okay. So I'll read from a book here, and then you guys can just follow along. But you guys obviously have done the exercise, so you know what I'm talking about. Okay, so number 3, just to put everybody in perspective, is that there are two beakers. There are two jars. Okay, they use beakers, the word beakers in the example, and that is that two beakers contain solutions of lead nitrate and sodium iodide. And so they give us as represented by this equation. So I guys want to adjust my light here a little bit. Here we go. It's represented by this equation, which is PB brackets NO3. There's a 2 there, so 2 nitrates there. And obviously that's in aqueous plus, and I'll put the balancing numbers in now. I'll put them in a different color. Sodium iodide, NaI, aqueous. Okay, that reacts and we get the products that form there are sodium nitrate, NaNO3, in aqueous solution, of course, and plus PbI2, which is lead iodide, and that's solid. Okay, let's see what color can we use here. Use 2 and 2, and we have a balanced equation. The information that they do give us in this little question here is that the volume of both solutions, volume is 300 cubic centimeters. All right, nothing to be afraid of there. And they also say here that the concentration of both solutions is 0.5 mole per decimeter cubed. When the two solutions are mixed, the mixture turns bright yellow. The reaction takes place given the equation, which I've already put there. And 3.1 was what causes the bright yellow color of the mixture. Okay, because they are mixed together. So when they are mixed together, it turns bright yellow. Okay, we need to obviously give the answer for that. Causes it to turn bright yellow. So for 3.1, what do you think is the correct answer there? Okay, it's one of these substances here, of course. So it has to be one of these products over here. Okay, what causes the bright yellow color of the mixture? Okay, because when they are mixed together, okay, they form this. So this is an aqueous solution. And they want to know what forms the bright yellow. Yes?
I was a bit confused at that question,
Okay.
but wouldn't it just be the solid?
That would be correct.
Or the solid affects the color.
Yes, that's right. So the solid basically is anything that does not mix, okay? Anything that does not mix. For example, if I can use the basic example, you order, okay, I'm not sure how much you people love your coffee, but I mean, you order cappuccino, right? And let's say, for example, the cappuccino was made similarly like this example up top here, it was just mixed together. Obviously, cappuccino comes with froth, correct? Froth. Now, the froth would act as, for example, like a precipitate, all right? Because it's not mixed in the mixture, right? Even if you stir, the froth doesn't necessarily mix after. It takes a while eventually. It's a stupid example, but I'm trying to get you guys to understand that whatever does not mix and whatever's not in aqueous turns out to be solid, okay? It might not be, for example, like a stone, but the thing that is causing the bright yellow color is what is known as the PbI2. You mentioned the solid, but it's called a precipitate. Okay, precipitate. Okay, so this word is vital in your answer. The lead iodide precipitate, but which is ultimately, as Matthew said, it's the solid that's affecting the color. Okay, if you said the solid, I think they would have still given you the mark, guys. Okay, if this was in an exam situation, I think you might have still gotten the mark. If you said the solid and then you put in brackets, for example, like this, PbI2, I think they still would have given you the mark.
Okay.
Let's have a look at the second question. 3.2 was rewrite the reaction equation as an ionic equation. Okay, because obviously it's not written as ionic yet. All right, so all we have to do is just rewrite it. So if we rewrite it as an ionic equation, you're going to have to separate some of these bad boys up. Okay, firstly, we can see here that Pb, all right, makes 2 bonds. All right, that's why we'll makes two bonds and nitrate makes 1. That's why we have one lead, which is Pb, and we have 2 nitrates. All right, so we know that Pb, and let's see if I can color code this, is going to be a 2+ ion. All right, use white for the plus signs. We know nitrate, we'll use green for that, is NO3 minus. Okay, that's the easiest part there. We separated those two. All right. Now we need to take care of the sodium and the iodine. Okay. Sodium we know. I'll color code again. Is a positive in a positive ion. Plus iodine would have to be opposite because it's in, I think it's in group 7. So that becomes I to the minus. Plus, oh no, we don't have a plus there. That tends to, now we've got to break up these components into ionic compounds as well. Na still is a positive ion, it's Na plus. All right, plus NO3, which we know is still the same as well, which is NO3 minus. All right, plus, you've got to break up the Pb solid as well. All right, let me just check. Yes. Okay, plus the Pb. I'm going to use the solid just as white as well. Pb, that's a 2+, just like this one over here, plus your iodine, which is I to the minus. All right. There's your ionic equation. All done. Okay? Except for one small thing that we forgot to do, was balancing. Okay? Now let's have a look here. What's the balancing number in front of NaI? All right, it's 2. All right, so if you break it up, NaI would be 2. That means it's 2 sodium and 2 iodine. So a 2 must go in front of this one, and a 2 must go in front of this element right here. 2 in front of the sodium, and a 2 in front of the iodine. Okay. Also take note, people, there is 2 nitrates as well. Can we see that? So a 2 needs to come in front of the nitrates because there's 2 of them. Okay. On the opposite side, if there's 2 here, well, must be 2 here as well. Those are now balanced in terms of ions, and there's 2 there, and a 2 must be balanced here as well. Okay. A 2 must come in front of the iodines as well, because we can see there. So if 1 lead, 2 nitrate, 2 sodium, 2 iodine, 2 iodine, ionic equation, done and dusted. Capiche?
Cool. Yep.
All right. Okay, so when you're putting together, as the question asked you, in an ionic equation, all right, you need to just separate. Like, for example, as you can see, all we did was just break up the compounds. We just broke it up. All right, that's all we did. Okay, that's what you'll be required to do even in the exam as well. For 3.3 said, will all the lead and iodide ions be removed from the mixture by the formation of a lead iodide precipitate? If not, which of these two ions is present in excess mixture? Okay. Again, let's have a look at that question again, because that was quite a mouthful. There's almost 2 questions involved in that one question. Okay, the first question they asked us was, will all the lead and iodide ions be removed from the mixture by the formation of the solid, which is Pb I2? If not, which of these two ions is present in excess in the mixture? Well, because we know how to approach a mixture question, okay, what we're going to do is we're going to first write down what we know. Remember, both solutions of the reactants, okay, the Pb, the lead nitrate, PbNO3, as well as the NaI, sodium iodide, have the same volume as well as the same concentration. So hence, if I work out the number of moles, it'll be the same for each. So for both solutions, okay, I'm just going to say both solutions, N is equal to C times V, okay, which is equal to the concentration of 0.5 multiplied by the volume in decimeters cubed. So I need to divide 300 centimeters cubed by 1,000 to get 0.3 decimeters cubed. And that gives me a number of moles of 0.15 mole of each solution. All right. So they asked for the ions. So we are paying attention to this equation over here, no longer the one that was on top here. So we discard that one, and we, for the question of 3.3, we're looking at this one over here. Okay. So since the 2i to the minus 1 there, ions are used for every 1 Pb 2 plus ion. So I can see over here that 2 iodine ions or iodide ions are used for every 1 Pb2 plus ion. All right, I can see that, okay, because it's in the ratio of 1 is to 2. All right, and even on this side, it's 1 is to 2. Okay, but more or less, but more so, we are dealing with this side because we're dealing with I2. So since there are two iodide ions for every 1 lead ion, 0.15 moles of the iodine ions will only use 0.075 moles of the lead 2 plus ions. Okay, so if we take that answer there, which is 0.15, and we divide that by 2 times 1, we can see that the lead, sorry, I keep getting confused with these names, please just bear with me, that the lead ions, all right, is only using 0.25. So if you got lead, 2 plus ions, and we got the iodine minus 1 ion, that's in a mole ratio of 1 is to 2, all right. For the mole ratio, well, the number of moles actually, this is the mole ratio. For number of moles, we've calculated 0.15. So lead is only using 0.075 moles. Right, so 0.15 moles is being used for every 0.75 moles of lead. All right, so iodine is using twice as much just to be able to cooperate or to be compatible with lead. So therefore, our answer, we'll be looking at our answer, because the answer is like which of these two ions is present in excess. It is clear that the Pb2 plus ions are in excess. All right, do we see that by looking at this little explanation over here? Can we see that? Is that clear enough
Yeah.
for everyone? Okay, it's clear enough for everybody? I just wanted to make sure that it's clear enough for everybody. So when it comes to checking if they are in excess or not, okay, we always have to first calculate the number of moles. And it was easy because they had the same concentration and the same volume. All right, so we can clearly calculate how much they are, or how the number of moles of each solution. All right, so we can clearly see that it's only 0.15 moles of each substance is 0.15 was the number of moles of each solution before they were mixed. And when they're mixed together, all right, we can clearly see here that it's using twice as many moles just to keep up with lead. So definitely lead is definitely in excess. 3.4, which was the last question, was quite an easy question, was calculate the mass of PbI2, which is the solid that was formed. I don't think I need to do that question. All right, I'll write down the formula that we needed to use. We needed to use, well, if n is equal to small m over big M, that just needed to be rearranged to say, well, therefore the mass is going to equal to the number of moles times the molar mass, and therefore the mass that you should have gotten should have been around the lines of 34,58 grams. We all get the last one at least.
Yeah.
Fantastic. Okay. Obviously, the number of moles that you're using was this one. All right, 0.075. Of course, because we can see that it's just a 1 there. Okay. Perfect. That was question 3. I think we need to do question 4. That's most suitable. All right. Okay, question 4. So question 4 says 5 grams of sodium carbonate powder. Okay, so we got Na2CO3. Okay, that's solid. Okay, and the mass of Na2CO3 was 5 grams. I'll add it to 400 cubic centimeters. Okay, volume 400 cubic centimeters, which is 0.4 decimeters cubed, and its concentration of 0.3 mole per decimeter cubed. Solution of hydrochloric acid. All right, plus, not plus, yeah, is plus HCl. Okay, in aqueous. Immediately bubbles are given off. This reaction takes place and is given by the equation, which I will now complete. NaCl aqueous plus CO2 gas plus, I'll have to write it underneath here, H2O, which is our liquid. And we're just going to balance this bad boy quickly. All right, let's see what we got here. We got Na2CO3. We got 2 Na, so I need to balance this side first. 2 sodiums, but now I have 2 Cls, and I need to put a 2 in front of here to balance my chlorines. My chlorines have 2 in front of them now. They are balanced. My hydrogens are balanced. So this is 2 and 2. My equation is now balanced. Will all the sodium carbonate powder be used up? And we need to show our calculations for that. Okay, so sodium carbonate powder, we are only looking at this one. Okay, I want to know if that's all going to be used up. So first of all, of course, you need to work out the number of moles. Okay, so the number of moles of Na2CO3, right? That is given by the mass, which we know is 5 grams. Okay, that needs to be divided by the molar mass of the substance. Okay, so it's going to be quite a long one. So let me just extend the line there. So I've got 2 sodium, so that is 2 times 23 plus 12 for carbon, and we've got 3 oxygens, so it's plus bracket 16 times 3. Okay, even a longer line. There we go. And it's 5 divided by that. Therefore, number of moles should equal, well, that's equal to 5 over 106.
0,047.
0,047. Well done. Thank you very much for that answer. Okay. So that's the number of moles of sodium carbonate. And they want to know, will all the sodium carbonate powder be used up? Show our calculations. Okay. So we've shown the number of moles, and we see that because of this mole ratio, we have 1 mole of Na2CO3 needs twice as many moles of hydrochloric acid, all right, in that mole ratio. Therefore, if this is the number of moles of Na2CO3 that is present, that means the number of moles, all right, I'll write that full out there, number of moles of HCl that is required then, all right, is obviously double 0.047 because it's in the ratio of 1:2. Okay, so if we double that, that'll be roughly 0.094 mole. Okay, so if we must, okay, let's just check. Let me just check something quickly. I sort of check my calculations out. I think I might have made a mistake. Times 2. Okay, no, that's right. 0.047. Okay, that's correct. So it needs double that. Okay, so therefore we can see that definitely by the means of this calculation, all right, that there is an excess of HCl. How we can check that, if there's an excess of HCl, okay, is to, all right, let's see quickly, need some remorse and say, okay, just checking through my solution here quickly, guys, give me 1 second. The one part that I did forsake is they've told us the concentration of hydrochloric acid. So we want to check that this conclusion that we've come to is true. So we want to check, okay, so for HCl, we just want to be sure of ourselves, of course. We want to check that for HCl, okay, the number of moles of the solution that is already present is equal to the concentration times the volume, which is equal to 0.3 multiplied by 0.4, which gives us 0.112 mole. Okay, so that is the number of moles that is present in the hydrochloric solution or hydrochloric acid, right? So there is only 0.112 or 0.12 moles of HCl there. So therefore, if we say that HCl, the number of moles of HCl that is required is double that of sodium carbonate, that means we are going to have an excess of HCl, all right? So therefore, the answer is, will all the sodium powder be used up? The answer would be, yes, it would be. Therefore, yes. That's all you have to say is just yes, or yes, all the powder will be used up. Because present in the solution, there's 0.12 moles. Okay, 0.12 moles is obviously bigger than 0.047. All right, 0.12 is bigger than 0.047. Might not look that way because you see 47, but because there is 0.112 moles of HCl, means there's excess HCl. So therefore, all the moles or all the powder of Na2CO3 is going to be used up. Any questions before we move on? Did everybody arrive at that conclusion?
Yep.
Yeah.
All right, good. So just to go through the steps of that question again, because obviously it's actually quite a nice exam question, except in the exam they'll probably just make it just a little trickier. But it's a nice exam question. First step actually should have been to check this, right? Check the number of moles of HCl that is present in the solution that you already have, which was 0.12. All right, 0.12 moles. Then we check, okay, well, what is the number of moles of the 5 grams of Na2CO3 that we want to obviously add? Okay, well, that's only 0.047 moles, okay? Quite a small number. It's not even close to a half yet, okay? Or even remotely still far from even 0.1. So now we see the mole ratios in 1:2. So that means for every 0.47, the number of moles that is required for HCl to react here is 0.094, right? And we have 0.112 moles of HCl solution, which means definitely, because this is so little, it's definitely all going to be used. There won't be any excess powder at all. It will dissolve immediately, which we can also see in the reaction as it has. So that was a nice question. That was a nice exercise. Hope you all enjoyed it as much as I did.
Yeah.
Good. Right. We're going to move on to possibly which is a firm favorite section for us as physics teachers, tutors, to teach and as well as to ask. All right. Percentage yield and percentage composition. Okay. Percentage composition as well as percentage yield, but we'll have a look at percentage composition first. Okay, there's two types of things that we're going to deal with here in this section. First is the two types of formulae. There's something that's known as empirical formula. You may or may not have heard of empirical before, as well as molecular formula. Okay, so the empirical formula, okay, this is known as the simplest ratio. Okay, the simplest ratio in which elements of that compound have joined. Okay, the simplest. Molecular formula may be a multiple of the empirical formula. Okay, so this is a multiple of empirical. In other words, it is the entire formula of the molecule that would be represented in a chemical equation had all the elements bonded with each other. So for example, if we have a look at the compound benzene, all right, benzene, all right, and the empirical formula would be, and I'm going to use a color for this, CH. That would be the empirical formula. But the molecular formula, as we would write it, is C6H6. How do we get the empirical formula here? All right. Well, we can clearly see that I have six carbons to 6 hydrogens here. We'll divide them all by 6 to get into the ratio of 1:1. This makes sense. That now that, well, you roll a nice line at least. That is that, but in simplest form. That's all. That's all we're doing here. All right. We're not trying to do anything else. Okay. That's percentage composition. All right. Or empirical formula rather. And the molecular formula. That's the difference between them. So don't worry too much about it now. We're going to have a look at a couple examples and how we can calculate it and how these questions will be asked in an exam setting. Okay. When it comes to percentage composition, which is what we actually want to look at here, okay, we are trying to calculate of what percentage of this compound is a certain element. All right. What percentage of this compound is, for example, we look at water, what percentage of that compound does oxygen take up? What percentage of that compound, which is H2O, that molecule, what does hydrogen take up in terms of percentage? All right, obviously we know percentage is easy, it's out of 100. All right, so let's have a look at an example. If we want to determine the percentage of water of crystallization in copper sulfate. Now, when you see something that looks a lot like this, boys and girls, is that when you see a compound that looks like this is copper sulfate, but we want to determine the percentage of water of crystallization in copper sulfate crystals. So if we have a look at the formulae or the molecular formula for copper sulfate crystals, the formula for that would be CuSO4. Sorry, that must be written a little closer. You'll see this little dot in the middle here. 5H2O. Okay, when you see this, okay, you know already that there's some type of crystallization that has taken place here. Okay, the first step to do would be to calculate molar mass, all right, of the specific compound. So the molar mass of copper sulfate water, all right, of water crystallization within this. Okay, so I want to calculate the molar mass of this entire thing. So let's do that. Well, we know that for copper, 63,5 on the periodic table, plus 32, which is sulfur, plus 4 times 16, that is for my oxygen, all right, plus 5 times, okay, we know that we can work out the molar mass of water already, which is easy. It's just 5 times, 1 times 2 is 2, plus 16 is 18, so 5 times 18, because I got 5 water compounds, of course. If we do that, that'll equal a entire molar mass of 249.5 grams per mole, just under 250. Now we want to know what percentage of water is water crystallization. Someone tell me what is 5 times 18?
90.
Thank you very much. So how are we going to do that? So this is where I'm at over here. So percentage of water crystallization, I'm just going to shorten it to Chris, is calculated by taking, well, the molar mass of water within this compound is 90. The total molar mass of this entire bad boy is 249.5. So if I perform this little calculation on my calculator, I'll get a percentage. Obviously, I'll have to times by 100, of course. Don't forget to times by 100 to get into a percentage. I'll get an answer of 36%. Right? So therefore, the answer of the percentage composition of water crystallization in copper sulfate or copper sulfate crystals, I'll be with you now, is 36%. Yes, my boy.
You mind repeating most of what you said just now? Like a large storm of hail just came and I couldn't hear anything.
Oh, sorry about that, buddy.
It's cool.
Okay. What I was gonna say it again anyway. So don't worry about it. So we just looked at a very simple percentage composition exercise or example, okay? They asked us to find the percentage of, determine the percentage of water of crystallization in copper sulfate crystals. Copper sulfate crystals, I just want to get rid of this M quickly. You're in front of Cu and write Cu just a little closer to SO4. This is the molecular formula or chemical formula of copper sulfate crystals. But we can see that the copper sulfate crystals contains a bit of water in them. So they want to know, in these little crystals that I have, because they're already crystallized, I have crystals, I'm holding them, okay? They want to know what percentage of these crystals actually is made up, or what percentage of these crystals actually contains water, all right? Water in them, okay? If I take one little crystal, okay, this will be the chemical formula of one crystal, okay? But there's some water in there, okay? Now, all compounds in percentage, obviously we know must add up to 100%. We know that, okay? So what percentage of this crystal, copper sulfate crystal, is made up of water? Well, first of all, if it all adds up to 100, I need to find out what is the molar mass of this entire little compound here, CuSO4.H2O, all right? It has 5 of them, okay? I need to find out what is that percentage of water. So I calculated the entire molar mass of CuSO4.5H2O, which happened to be 249.5 grams per mole. Out of that, the molar mass that was water, the amount of the molar mass of water was 90. So if I want to find out, okay, what percent of that is water? Well, 90 divided by the entire molar mass, so the molar mass of water divided by the molar mass of the entire compound, times 100 will give me what percent of that is actually water. Once you perform that calculation, we get that the percentage of water of crystallization, or the percent of water that was crystallized along with the copper sulfate, is 36%. Does that make sense? Everybody get that?
Yeah.
Good, lovely. Now that was a basic one. Still a nice little exam question that they can throw in after asking you a whole bunch of other jargon and other bunch of questions. There's a nice little way to end off a question. What percentage of water? Okay, but they might have asked you a little other questions before that. So this might be like 3.3 or 3.4. But now we have another type of example where now they start off the question by giving you percentages. And now, as usual, most students, what do? They panic. Okay, so what do? They panic. Okay, so what do we do here? Everybody can still hear me, right?
Yeah.
All right, cool.
Yep.
Okay, so what we do here is we have a mass of a compound. They say we have a mass of a compound. What compound? We don't know, but they tell us that the mass of a compound is made up of, and this is where the fun bit comes in, 30.4% nitrogen, all right, 69.6% oxygen. Now they ask you to determine, number one, empirical formula. And number two, they ask you to also determine the molecular formula of the compound if the molar mass of the molecular formula, now not the empirical formula, the molecular formula is equal to 92 grams per mole. Now that might look like quite a stinker of a question, but believe it or not, it isn't. All right, we start with the simplest thing first. All right, so for the given that we have, the information that we are given, for the given information, we know that in 100 grams of the compound, there must be 30.4 grams of nitrogen and 69.6 grams of oxygen. All right, so we take the percentages here as the mass value for number one. So for 100 grams of this particular compound, all right, in 100 grams of that, okay, we know that 30.4 grams must be nitrogen. And we also know that 69.6 grams must be oxygen in 100 grams, okay? Because if that's how it is in 100%, then, well, in 100 grams, that should be it, because it's going to add up to 100, okay? So what do? We can determine now the mole ratio of each of the elements in the following compound, okay? We want to calculate the moles of nitrogen in 100 grams. Right? We know that as N is equal to M over capital M, well, 30.4 divided by, well, I know the molar mass of nitrogen is 14. That gives me 2.2 mole of nitrogen. And now the same thing, the moles now of oxygen in 100 grams. These quotes are saying, same thing as above. The same formula over being M, 69.6 over molar mass for oxygen, 16, 4.4 mole. So I can clearly see by looking at this that this is double that. So the number of moles, or the ratio, all right, of nitrogen to oxygen is 1:2. Correct? I can see that. 2.2 times 2 is 4.4. So I can see, okay, well, that's 1. Okay, well, that's double that. So it's in the ratio of 1:2. So therefore, the empirical formula for number one, therefore, empirical formula must equal, or should be, N is, well, 1, NO2. Questions?
No. Simple. I know.
Simple is what I like to hear. Okay, let's have a look at number 2 now. I'll bigify my eraser. So when you are given, for example, the percentages, just like in this example, and you're asked to determine empirical formula, we interpret that the percentages as grams in 100 grams. So we had 30.4% of nitrogen and 69.6% of oxygen. Well, if those two add up to 100, then that means, well, in 100 grams, it'll be, well, 30.4 grams and 69.6 grams. So always assume for 100 grams if you need to find out the empirical formula. Number 2 was the molecular formula of the compound. If, and I do say if, all right, the molar mass of the compound was 92 grams per mole. So we know that the molar mass of our empirical formula, okay, we just calculate an empirical formula to be NO2. Okay, we need to know, okay, well, what is the molar mass of our empirical formula, which is clearly equal to 14 plus 2 times 16. Okay, 14 for nitrogen, 16 is oxygen, but there's 2 of them, so you multiply them by 2. The molar mass that we get is 46 grams per mole. Okay, well, since the molar mass of the compound for molecular formula is 92 grams per mole, okay, this is of the molecular formula, and the empirical formula is 46 grams per mole. Can I see, based on just my knowledge and maths developed brain, because I'm in grade 11 now, my brain is developed over time, that 46 grams per mole is clearly half 92? Can I see that? Of course I can. All right? I can see that it's half. So that means the molecular formula is just double that of the empirical formula. Okay? And we know what the empirical formula is. The ratio was 1:2. So if we multiply both sides by 2, what do we get? We get a molecular formula ratio of 2:4. Therefore, without even doing much of a calculation, the molecular formula is N2O4. Any questions?
None from me.
None from you. Okay, cool. Fantastic. Okay, that's about just one of the aspects that we're going to do. And I need to just teach one more thing before we can go ahead and have a look at an example. So if you guys track with me as well as you have been, then we surely will be able to finish the sign. And then next week we start with, well, we'll go through the exercise next week and then we start with a new topic. The last thing, percentage yield. Percentage yield. Now, the maximum quantity of a product that can be obtained from a chemical reaction is known as a theoretical yield. Okay, we have a word theoretical. Okay, as you can say, most of the stuff that we do in high school, especially in high school physics or in physics in general, is theory. But then, believe it or not, for every theory, there's an actual, there's a definite. Okay, it's known as the actual yield. Because in practice, there's invariably some waste in the isolation, and there's purification of products. Okay, in other words, there is some other type of process that does occur whenever we deal with reactions in theory. We are assuming that the reaction is going to go exactly as we want it to go. So there's going to be no presence of anything else. There's no dirt in the beakers that we use. There's no presence of any other previous substances that could possibly react and could possibly influence the reaction that we want to achieve. That is called the actual yield. It's the quantity of a product that is actually obtained in the laboratory. Okay? And sometimes the actual yield, most often than not, is less than the theoretical yield. So in theory, we should get, for example, 74 grams per mole or 74 moles of a substance, but actually we get 70. Okay? So we're going to have a look at how we can determine the percentage yield of a certain reaction. That is given by a certain formula, guys. Let me just change the color, sorry. Which is known as percentage yield. Often when I used to write down this formula, I would just write the percentage sign. Percentage yield is perfectly okay. We have the actual yield divided by the theoretical. Multiply that by 100 to get the percentage yield of a reaction. Let's have a look at an example. I'm going to write down a reaction that takes place. Okay, CaOH solid plus 2NH4Cl, another solid, two solids reacting with each other. CaCl2 plus 2N, that's shockingly awful, 2NH3 gas, ammonia gas, plus water. Okay, you obviously know it's liquid. Right, that's our reaction. In a laboratory experiment, ammonia gas is produced and collected using the apparatus. All right, so if I must draw an apparatus here quickly, we have our Bunsen burner at the bottom. There's a flame there, okay, and it's in a beaker along the side like this. Okay, the tube is inside, which will be like a funnel going inside a gas jar. Okay, this very rough drawing. Okay, we have our gas jar, which will obviously collect the gas. This is known as a funnel or delivery tube. Okay, this one is obviously known as our test tube, where we test our substances. Okay, and we obviously have the two solids mixed together, which is calcium hydroxide powder and ammonium chloride powder that are placed and mixed in the test tube. And here we obviously have our Bunsen burner, which I don't need to label. It's very clear. When the mixture is heated, the following reaction takes place, as I've already drawn. Okay, the mass of calcium hydroxide which reacted is 40 grams. Okay, new bit of information there. Mass of Ca brackets OH that reacted is 40 grams. So the 40 grams of this powder, it is found that only 21 decimeters of pure ammonia was produced. Okay, so the volume of ammonia over here was only 21 decimeters produced. Assume the volume is measured at STP. Calculate the percentage yield. Okay, first things first, we don't panic. Okay, we know exactly what we're doing. We have everything that we need. First things first, we're going to work with the calcium hydroxide. If I've got a mass here, I need to calculate what's the molar mass of that, so I can calculate the number of moles. So that was the mass of CaOH2, but now the molar mass of CaOH2. Okay, let's calculate that, which is the molar mass of calcium plus 2 times 17, because the molar mass of our hydroxide is just 16 plus 1. So I have 40 plus 2 times 16 plus 1, which is 2 times 17, gives me 74 grams per mole. Everybody can see that. Hence, the number of moles is mass divided by molar mass, which is 40 divided by 74, which gives me 0.54 moles of calcium hydroxide. Okay, now we don't know, all right, we don't know what is the volume of, or should I say, we don't know what is the number of moles of NH3. Okay, because that's what we're obviously comparing it to. Okay, but we can see that for NH3, the mole ratio of Ca to NH3 is in the mole ratio of 1:2. Okay, so I have 0.54, all right, equals X, well, that's over 1, my mole ratio, equals X over 2. All right, therefore, X, which will obviously be the number of moles of NH3, obviously I need to multiply this side by 2 to get rid of that, is obviously twice that of calcium hydroxide. Therefore, X is equal to 1.08 mole. So for every 1 mole of calcium hydroxide, 1.08 moles of NH3 is produced. can see that. Okay. They also told me that the volume produced was 21 decimeters cubed. Okay. So we need to calculate what was the theoretical yield, because we have the actual yield was 21. So what in theory should have actually been produced if this all went according to our theory? Well, what we do, we know the number of moles is also equal to, and let's see, should I squeeze it in or should I'll try and squeeze it in. You guys can always tell me if I must write it a bit clearer. 1,08 is equal to V divided by 22,4. All right. If we do that, therefore, the volume that we get in theory is equal to 24,2 decimeters cubed. That's my theoretical yield. Okay. Coming back to our example, we want to now calculate the percentage yield. So what do we have? We have the actual yield over here. Sorry, let me just get my pen again. We have the actual yield over here, and we've now calculated the theoretical yield. We can now go ahead and say, okay, well, percentage yield is equal to our actual divided by theoretical. All right, this formula times 100. Okay, I don't know what happened there, but anyway, times 100. So what we do then is we take 21, which is our actual yield, divided by our theoretical yield, which is 24.2, multiply that by 100, we get an answer of 86.8%. Okay, so instead of 24.2, which is obviously 100%, okay, that should have been the entire or the theoretical volume that should have been produced. All right, only 86.8% was produced. So not the full 100%, only 86.8%, right? Which is obviously 21 decimeters cubed was only produced and not 24.2. Okay, so you can calculate obviously the percentage lost, all right, which is obviously 100 minus 86.8, and that would have obviously been the number of, well, you can also take 24.2 minus 21, all right, take that amount divided by 24.2 to get the remaining percent or the percentage that was lost, if that is part of the questions. Boys and girls, any questions? Was this clear?
Yeah.
It's clear. Okay, I'm glad. If it's clear, then that means this is free marks in the exam. And we love free marks, don't we, boys and girls? We love free marks. Free marks is fantastic.
Yep, you're right.
Okay, so I don't know if you guys have your phones with you. I believe you should. I sent an exercise through, which is the final exercise, and it's on percentage composition as well as on percentage yield. Okay, if you guys can get that open, I'm going to try and send through a clearer document eventually, but I think that document is clear enough to at least perform. I'm just going to get it open. Where is it? No, that's the wrong group. Right, it's at least able to be, you guys should be able to see at least number 1, number 2, number 3, all the way through to number 6, and then it just gets a little unclear as you get to number 7. Okay, which is not to worry, I can always send through the 7th one again, so don't worry about that. So if you're looking at, okay, first of all, do we all have that document open? Do we all have that document open? Okay, if we do have the document open, I just want to go through, take, for example, number 1. Okay, this is of our exercise. Okay. Of our exercise. Okay, let's have a look here. Number one, they ask us to calculate the percentage of copper in each of the following copper compounds. In 1.1, they've given us the compound CuCl. Okay. Now, the first step in the solution here is always to first calculate the molar mass, right, of CuCl. Sorry, it's CuCl2. There's a little subscript at the bottom there. CaCl2. All right, CuCl2 rather. We need to calculate the molar mass first. So the molar mass of this substance, if you look on our periodic tables, all right, of CuCl2 copper chloride is 63.5 for copper, plus 2 times the molar mass of chlorine, which is 35.5. All right, we get a molar mass answer of 134.5. All right, we get 134.5. We know that 63.5 is the molar mass of copper present in copper chloride. So therefore, percentage composition, percentage comp, is equal to, well, this is of Cu, 63.5. Oh wow, that's hilarious. 5. That is divisible by 134.5, which is the entire compound. And out of that, copper only takes up 47.2%. All right, now that's basic enough. Now for 1.2, we've already done 1.3, so I'm going to omit 1.3 because I already did 1.3 with you guys. You guys can just fill in the same answer there. Cu, they asked the same thing, but now this is for Cu brackets NO3 2. So I'd write that one out to make that a little clearer for you guys. Okay, so now can we please calculate the percentage composition of copper for number 1.2? You guys can do this on your own, and I will take the answer in another 2 minutes. Get an answer of 33.87 or 33.9%. Now, for the second question, it says calculate the percentage composition of marble. Okay, CaCO3. Okay, what we've got to do here for number 2, all right, is calculate.
JP, we're not doing 1.3.
No, 1.3 we already did. Unless you want me to do it again.
Oh, I see. Okay, it's fine.
Okay, cool. So now for question 2, okay, let me just get back onto there. 2 CaCO3 is known as marble. Okay, that's marble. Okay, we want the percentage composition of marble, which is CaCO3. In other words, what we want to do here is we want to basically break up this entire compound into percentages. That's all we want to do. Okay, what percentage is calcium, what percentage is carbon, and what percentage is oxygen? That's all. All right, so what do? You clearly see that everything needs to add up to 100. Everything needs to add up to 100. Okay. What's the someone give me the molar mass of calcium, please?
It is 40.
40. Okay. Someone please give me the molar mass of carbon, please. 12. That's correct, thank you. And well, there's 3 oxygens, so that should be 3 times 16. If I add up this entire compound, the molar mass will be 100 grams per mole of marble. It adds up to a complete around 100. So because I know the molar masses of carbon and of carbon, calcium, and oxygen, for calcium, what am I going to do? 40 divided by 100 is 40%. For carbon, 12 divided by 100 is 12%. And oxygen, I have 3 times 16, okay, which is 48. Divide that by 100, I get 48%. Easy peasy, right? That's how you look at that question. When they give you a compound and they say calculate the percentage composition, what they want you to do is actually express that entire compound, all right, in percentage. That's all. Okay. So if it adds up to 100 grams per mole, then basically if I have 100 grams of a substance, okay, the molar mass should equate to the percentage as well. Okay, or the mass of the substance or the percentage of that substance should equate to the mass as well. Okay, in this case, the number of the molar mass of calcium is 40 grams per mole. So 40 grams per mole divided by 100, which is the mass of the entire marble. Molar mass of the entire marble gives me 40%. So calcium takes up 40% of that compound, carbon takes up 12% of that compound, and 48% of marble is oxygen. 40% of marble is calcium. Easy as that. Now we get to question 3, and now the heat is turned up a little bit. Okay, question 3, I'm giving you guys to do on your own. (3.1). All right, so we were given potassium. Okay, potassium was 31.8%. Chlorine was given at 29%. And the last one, which was oxygen, that was given at 39.2%. Okay, so how do we do this one? Well, this one we need to assume, all right, that 31.8%, 29%, and 39.2% all equate to 31.8 grams, 29 grams, and 39.2 grams. This is if this is in 100%, then this is in 100 grams of substance. Okay? So, what do we do here? Is let's see, we have 31.8. Let me just see if there's something I'm missing here. Okay, I just want to pull up a periodic table. That's the only thing I'm missing actually. And it's not at the back here. Where is it? Here we go. Periodic table for look at potassium. All right, which is the symbol K on the periodic table. It's just 31.8 divided by its molar mass, which is 39, times 100, of course. Oh, sorry, not 100, sorry. We need to calculate the empirical formula, so not 100. If we do that, we get an answer of 0.8. For chlorine, 29 divided by its molar mass, which is 35.5, gives us an answer of also 0.8. All right, and then also oxygen, we got 39.2 divided by its molar mass, which is 16, gives us an answer of 2.4. All right. This is for oxygen. This is Cl. This is for oxygen. Okay. So the ratio of K to chlorine to oxygen, all right, is, so we can see the smallest value here is 0.8, correct? All right, so we have 0.8 is to 0.8 is to 2.4. So what do? We need to make this into a simplest form. So we need to divide by the smallest number here, which is 0.8. If we divide by 0.8, we're going to get a ratio which is 1 is to 1 is to 3. Okay, so therefore, the ratio of K to Cl to O is in the ratio of 1 is to 1 is to 3, and therefore we must write that out as an empirical formula. Empirical formula is K ClO3. That's empirical formula. Who got that? Anybody?
I got KClO2.
Where did you go wrong?
Yeah. So when I was doing the division of the like the 31 over 0.8 over 39, I was getting a bit confused. I didn't realize that you had to put it over 39. I thought that you had to times it by 39 and like.
Okay, I see.
Yeah, so I got it a bit wrong. Oh, yeah.
We're close though.
And then my ratios were different.
We're close. Close enough.
Yeah.
Okay, but as you said, well, as it is, it's still incorrect. Okay, so always when you're trying to work out empirical formula, if you're taking these percentages which we had on top here to be the masses, we obviously need to calculate the number of moles by taking obviously n is equal to the mass over the molar mass of each substance. Okay, that's all we had to do, and I'm sure as you see now. So like I said, the nature of 3.2 and 3.3 is exactly the same as 3.1, exactly the same. So you guys should be, if you guys went wrong in 3.1 now, as obviously Matthew has come clean that he went wrong. Yeah, I'm not sure about the other two. But if you guys fall in the same boat as Matthew now, you can be like, okay, cool. I know what I did wrong. You can go and correct your 3.2 or 3.3. Or if you didn't start them yet, you can finish them and obviously get them correct by doing it in this fashion. Okay. I don't think we're going to have enough time to go through another question, but we can see that the molar for question 4. I'll get question 7 to you a bit clearer in like probably by the end of the day. But question 4 now, just want to go through it. So maybe if there's any confusion now, we can determine that. They say that the molar mass of a compound is 30 grams per mole. They give you the percentage composition of 80% carbon and 20% hydrogen. Determine the empirical formula and also determine the molecular formula. Now that's quite an easy question because it's exactly like the same question that we went through in the example. It's exactly the same. Okay, for question 4. Okay, you have the percentage composition, right? All you need to do for empirical formula is obviously calculate the ratio, the mole ratio, of course, and then that will be your empirical formula. So if you get an answer of, let's say, 1 is to 3, then it'll be obviously CH3. All right, for example. And for 4.2, you have to calculate the mole ratio or the molar mass of your empirical formula to find out the molecular formula. If you see that it's doubled, then you know that your mole ratio for your molecular formula must just be double. So for example, if you had CH3 the ratio is 1:3. It's doubled, so you must multiply it by 2. Then you get obviously 2:6. So your molecular formula may be C2H6, for example. Any last minute questions pertaining to this section? Because after we go through this exercise next week, we close the section. Any questions?
No, I think that's it.
Okay. All right. Cool. Thank you so much, guys. And I think we can end it there. I appreciate it. Okay. Thank you so much for coming. And like I said, any questions that you have when you're doing the exercise, just hit me up with the text. My number's available in the group, of course. And yeah, stay warm during this little cold weather. Hailstorm or heavy rain just hit the roof of my house now. So yeah, I'm jumping back into bed now. So for you guys, stay warm, stay safe, and we'll check you next week.
Cheers.
Cheers.
Okay, see you.
See you, man. Cheers.